Hello everybody, we're on 3.4 exponential decay. Alright, so we've done exponential growth, now we're going to be doing exponential decay. I'm on this page here of the packet, experiment heads or tails. We're going to skip the experiment, we're not in class. So I'm going to skip over to the next piece here and it's looking at this letter A, section A here. Alright, so we talked about cutting the ballots. And now we have another example similar to that. Okay, so we first look at the exponential growth when we looked at the number of ballots that we did in class. Now we're going to examine the area of each ballot afterwards, right? So first was we cut the piece of paper. How many ballots do we have? And it was increasing, right? It was like increasing exponentially. Went from 1 to 2 to 4 to 8 and so on, dot dot dot. And now we're looking at the area of the ballots. So I don't cut the ballot. I have 0. 0 cuts, my area is 64. I make one cut, now the area of one ballot is 32 square inches, or inches squared. And then I do it again, and I do 2 cuts, and now I'm down to 16. So what are you noticing that's happening, right? So how am I getting from 64 to 32 by multiplication, right? So what are we multiplying by? So I'm multiplying this by a fraction this time. So I'm multiplying by 1/2. 32 times 1/2. Now you could definitely be thinking dividing by 2, but remember, dividing by 2 is the same thing as multiplying by 1/2. Alright, so we're always going to look in terms of multiplication here. Alright, so how am I going to get to the next number here? Well, the next number is also going to be following that pattern of multiplying by 1/2, right? Multiply by 1/2 each time, and you'll keep going half of what you have, right? So 16, 8, 4, 2, right? 1, right? Multiply by half, 1/2, 1/4, 1/8, right? Just keep multiplying every time by 1/2, and I get down to 1/16 of a square inch after 10 cuts. All right, so how does the area of the ballot change? All right, so it gets cut. The area gets cut in half. And cut in half. Perfect. We'll take that. Alright, and it says write an equation here. Okay, so cool. So nothing changes for the equation, right? So f of x equals a times b to the x power. So I need a. So I'm going to go back to my table. Okay, so well, here's my y-intercept. So 0, 0, whatever that number is, that is my a. So my a is 64. Cool, I'll take that. And then my b value here is, remember, so this is the b value, that what am I multiplying by every time to get to the next number? So that's going to be my b value there, right? So that doesn't change either, but this time, this is my b. So now b is equal to 1/2. So now, my equation is f of x equals a, which is 64, times 1/2 to the x power. And this is what makes it an exponential decay. Right, so how is the pattern changing? Different. So the pattern is decreasing, right? In this case, how is it similar? It's decreasing, but we're still multiplying, right? Each one is still multiplying. We're still multiplying, so it's still a geometric series here, right? And how is the equation different, though? Right? This time the b value, or the growth factor, is a fraction. All right, and the b value, in order to be exponential decay, is always going to be, well, it's going to be greater than 0, because you're not going to have 0 to anything. And now it's going to be any number less than 1. And that's what will make this a growth factor, okay? A decay factor. I'm sorry, so the b, or not growth factor, let's get rid of that word and make this decay factor. Right, so the b value, or decay factor in this case, is a fraction between 0 and 1. Alright, so there's some differences, there's some similarities. I'm going to toggle to this next page here. Alright, exponential growth versus exponential decay. Functions. Y equals, get rid of that. So y equals a times b to the x. Cool. What changes in exponential decay? Absolutely nothing. Still y equals a times b to the x, right? So the format's still there. Have a growth factor and a growth rate. Yes, we have a growth factor and a growth rate. In exponential decay, we have a decay factor. So let's write that one in there. Keep this nice and neat. A decay factor and a decay rate. Okay, so we have a growth factor and growth rate in exponential growth. We have a decay factor and a decay rate in exponential decay. Okay, cool. The growth factor is always a number greater than 1. Right, so your growth factor or decay factor, or your growth factor says greater than 1, or b is always greater than 1, right? So the growth factor is b. And in this case, your decay factor, let's steal that word again. Decay factor is always a number between 0 and 1. So your b value is going to be greater than 0, but less than 1. Okay? So between 0 and 1. Alright, not including 0, not including 1 there. Alright, to find the growth factor when given the growth rates. Alright, so I'll give you a growth rate. So we had a couple examples of that. We just take the number 1, we add the rate, so whatever percent that was, so whatever n percent that was, and we have the growth rate, and we have the growth factor. So 1 plus n percent will give us the growth factor, right? That's my growth factor here. Now to find the, again, special word here is copy this one again, to find the decay factor when given the decay rate. Alright. So this time I'm going to start with 1 again, and this time I'm going to subtract whatever the decay rate is from there, and this will give me my growth factor. Or, I'm sorry, my decay factor, and I'll write that one out. Alright, so always starting with 100%, right? That's what this 1 represents, right? This 1 is my 100%, and then I add to it. Well, I'm starting with the same 100%, but this time I'm subtracting from it. Okay? And that's the difference between exponential growth and exponential decay. Okay, so let's take a look at a few of these. We took our time with exponential growth. I think decay is going to go a little faster, so let's take a look. A different flea market, different flea medicine breaks down at a rate of it breaks down at a rate of 20% per hour. This means that as each hour passes, 20% of the medicine is used. This is the rate of decay, right? So this is my decay rate, 20%. So the initial dose is 60 milligrams. Complete the table. Okay, so you have 60, and you need to decay 20%. So I'm going to ask you to think back to 7th grade here, right? So if you have 20%, so if you use 20% of the medicine, what percentage is left over? So here's your hint to 7th grade, right? So you start with 100%, right? If you use 20%, so if you use 20%, then you're only left with 80%. So 2 ways. You can find 20% of 60 first, right? And then that'll give you 3, right? 2 times 20% of 60. 2 times 6 is, just joking, 3. 2 times 6 is 12, right? 2 times 6 is 12, and 20% of 60 is 12, and then you can do 60 minus 12, and you get your next number, which is 48. Or, I'm going to scratch this out, and this is not the way I want you to do it, so getting rid of that, you could find 80% of 60, and this will give you the same number, right? 8 times 6 is 48. So finding 20% of 60 and then subtracting from 60 gives you 48. Or you can get there in one step, and that will give you that method here. So what I'm going to do is multiply this by 80% or 0.8 every time, and I'll get my 48 again. So I'm going to multiply down by 0.8 every time as I decrease. So 60 times 0.8, my decay factor, right? The decay rate was 20%. The decay factor was 80% or 80.8. So if I do this again, I get 38.4, and again I'm going to multiply again by 0.8 or 0.8. I get in there, and I get 30.72, and again this is just giving me 80% of the number every time I multiply down. So this would give me 24.576, and my decimals are going to get a little bigger here. 19.6608, and then one more, why not? And then times, and I get 15.72864. Alright, so your decimals are going to get longer as you go, and I'm not expecting you guys to write decimals. So at some point, you're going to round somewhere, and the more decimal places you use to round, the more accurate your answer will be. So if you start rounding to the tens place only, your numbers will differ a little bit from mine or from your classmates. I think a good rule of thumb would be if every rule rounded down to the tens, hundreds. Let's go to thousands place. I think that would be tens, hundreds, thousands, a good safe bet to try to get a good answer. All right, so there's our table doing this. All right, and then for the medicine, Janelle wrote an equation, 60 m of H equals 60 times 0.8 to the H power to show the amount compared to quantities active, and then we're going to give our table here. So let's see what this looks like. If we count by 10, 20, 30, 40, 50, 60, that would still get me there. If I did fives, 10, 20, 30, 40, 50, that's only giving me 50s. I'll do tens, that's fine. So 10, 20, 30, 40, 50, 60. All right, and I'm going to start with a y-intercept, and this is my, we have time and active medicine. So I'll just abbreviate active medicine and the time here. So at time 1, time 0. At time 0, we're at, here's 0, 1, 2, 3, dot, dot, dot. And let me just get rid of this. So looking at the table, my y-intercept here is 0.60. All right, so let's get that 0.60 on there. Here we go. Sorry about that. Here's 0.60. All right, and then at 1, we're at 48, which is right around here. And then we're going to keep going down. At 2, we're at 38. 2, we're at 38.4. So at 38.4 is right around there. At 3, we're at 30.72. So at 3, we're about 30.72. Then we have 4, 24.576. So about 24, 25-ish. At 5, 19.666. So about 20. At 6, we're at 15. So about right here. And what you're going to start seeing is this coming down, 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 down. All right, so this is what's going to happen here. And obviously this is getting cut off in the first quadrant here, but if this continued into the second quadrant, then this would follow up and be coming this way. All right, so I'm not including that green part there because it's not part of the domain, right? I can't go into negative times, right? So that's only the first quadrant. But if it was to continue, then the exponential decay versus the exponential growth. Exponential decay is coming, right? They still have a y-intercept, and it comes down, and it goes down this way. Right, so exponential growth, just to recap, was going very low and then shooting up, right? That was the growth. And now we have our decay graph, right? So this is the difference between those two. What's happening here is this is your x-axis, this is your y-axis, and this is actually a reflection over the y-axis, right? So this graph was just reflecting over the y-axis, right? It's a mirror image of itself, just reflecting over the y-axis, all right? So that's the difference between growth and decay. All right, and then we'll keep going and see what else we got here. So we got Dwayne, and Dwayne was confused by the terms of the and do you agree with him? So because the decay rate is 20%, the decay factor should be 0.2. That's not true, right? The decay rate is 20%. So imagine going to the mall and you have, you're buying a $100 pair of jeans and it says 20% off. Well, are you going to the cashier and saying, here's 20 bucks? You might like to, but the answer is no. You're not going to go there with 20 bucks. It's 20% off. So I'm going to take 20. So 20% off out of 100 is really just 100 minus $20, which will give you down to $80. So that's pretty much what it's saying here. So if it's 20% off, then what percent are you paying? Well, 20% off means I'm paying 80%, right? So if I'm paying the 80%, that is the growth decay, right? That's what I can multiply by 100, my original number. So 80% times 100, and I'll get straight to my answer of $80, right? So if you want to think about it in that sense. All right, so that's why this is incorrect. All right, and then Stephen recalled that when the growth rate is 80%, the growth factor is 1.8. How is the relationship between growth rate and growth factor similar? And between decay rate and decay factor, right? So we're always starting at 100% no matter what. And if it's a growth rate, right, growth, we're adding 80%. And we get to the 180. And if it's a decay rate, I'm going to decrease. The decay rate was 20%. I'm going to decrease 20% from, again, always starting at 100%, right? So you're always adding or subtracting either in the growth factor, right? In growth factor, I'm adding. In the decay factor, I'm subtracting or decreasing from 100%. Right? Growing from 100%, decreasing from 100%. Right? And there's your similarities and differences. All right, so that's the part B there on your page here. And I just, actually that was part C, sorry, so I must have skipped a page there. Sorry about that. I think I skipped part B. Hopefully we'll find that somewhere, but if not, no big deal. All right, so that was part C. You could try part B on your own and go from there. All right. All right, guys, so I was just looking at my slides here, and I did actually skip over part B. Sorry. Let's finish this up. We'll do part A, B, and C in one swoop here, and then we'll get through this a little faster. So fighting fleas is, so the other one we had to make the table. This one they actually gave us the table, so this one's going to be a little easier. All right, and how does the amount of inactive agreed change from 1 hour to the next? So from 400 to 100, right? How are you changing? So you're at 400, you're multiplying by some number, and you're getting to 100. So how are you getting there, right? So this is one way you could do it, which is similar to the formula that we did with the exponential growth. So you still get 1 over 4 here, right? So your decay factor is 1/4 or 0.25, right? Is the decay factor. All right, and write an equation for all this. All right, well, for an equation, I need a y-intercept. So my a value is 400, and I need to know what I'm multiplying by every time to get to the next number, the growth decay. The decay factor. So my b is 1/4. So now I got my f of x equals, I got a times b to the x power. Beautiful. And so let's finish this off. F of x equals 400 is my a times 1/4 to the x power. And this is the graph that goes with that. And if you're noticing, it's going down at an exponential growth. Alright, so in this graph has a similar to the problem we just did. Well, they both go down. They're as the time goes by, your values, your y values are decreasing and decreasing throughout, right? And does the relationship in the table represent an exponential function? And the answer is yes. It has the model. It's a function because it passes the vertical line test anywhere you draw the vertical line. Right, so any one of those could be reasons for it, right? You're multiplying by 1/4, so this is the geometric piece here. So your y values are decreasing by a multiple of 1/4. That's what makes it a exponential and not linear or anything else. All right, and I think that's one thing. We got one more question here. I think that's about it for part B. All right, so let's do a quick little comparison of exponential growth and exponential decay. Sorry, this video is a little longer than the other ones. Promise to try to keep them down. And then we'll do a little more practice on the next day for decay rate and decay factor. All right, guys, have a good day. Talk to you soon.